So today did anybody, oh, we have an assignment that's due, and so I should start with questions that any of you might have on that. The Chapter 7 assignment. It wasn't very heavy on calculation. As I told you, this chapter was different, in that you had to do, I don't know, it's just more on procedure, removing bias. You guys did have to use a random table in some problems. Had to recognize certain kinds of errors. Yes, Mark.
I'm not sure about 35.
35? Well, let's take a look. If I can get there. 735. Sampling college faculty. Labor organization wants to study the attitudes of college faculty members toward collective bargaining. These attitudes appear to differ depending on the type of college. The American Association of University Professors classifies colleges as, and then they give these different classifications. Discuss the design of a sample of faculty from colleges in your state with a total sample size of about 200. So, you're probably wondering, why did they give me those classifications? I think they were trying to set you up, Mark, to make use of a stratified SRS. And so, I'll tell you what I wrote down is use a stratified random sample, and then what I would do is pick an SRS from each of the strata in proportion to the current populations. Now, I don't think we know that right now, but in other words, if I knew that, let's say, class 1 was the biggest, then I would want to make sure I have I'd want to pick the bigger SRSs in the bigger populations to try to keep a true proportional representation. Now you've got a nice stratified sample. I think that's about all you can do here, except that the total SRS is supposed to be 200, so I'd take this 200 and I'd divide it up according to those. I think something like that's probably what they were looking for. So, do you have to do a stratified random sample? No. Why do we do it? Because besides telling you about the whole population, it gives you more detailed information. There might be some bonuses in there, like, holy cow, do you believe what happened to class 2A? The surprise that, you might find that that particular class yielded something you didn't even expect. So you get some specific bonuses sometimes. Other questions on Chapter 7 assignment? Darnell?
Number 11.
11, okay.
I don't understand what they're asking.
Yeah, what are they trying to get at? Well, let's see. First I have to find it. Okay, we have a club that has 30 student members and 10 faculty members. They give you the list of the students, they give you the list of the faculty members. It says the club can send 4 students and 2 faculty members to a convention. It decides to choose those who will go by random selection. Use Table B. So, you got here, what you need to do, first of all, Darnell, is pick 2 separate SRSs, because they've already divided them into 2 groups. From that first group, you're going to pick, what was it? 4 students. Okay, now, were you here when we did the table thing? Okay, so you don't need me to go through that? It doesn't say where to begin, so pick some line on Table B. Start cranking away until, oh yeah, and you remember, to use the table properly, you really have to number the students first, and then keep going until you get 4 of them. And then start over, do the same thing with the faculty members. Doesn't matter if you begin on the same line of Table B or a different one. I think that's pretty much it, just two separate SRSs. So it's kind of like in one hat, you're picking out student names, and in another hat, you're picking out faculty names. Jennifer?
I just had a question on 745.
Question 45, okay. I'll head there. Yeah, sampling retail outlets.
I just wasn't sure what the applet to choose the sampling.
Okay, you got to go to the, what you do to get those applets, I'll show you what you need to do. You go to the My WLC. Just take a few seconds here. Anyway, on that page, and it should be right under this Chapter 7 section, you should see something about an applet, I believe. We'll find out. If not, I'll show you how to get there. That wasn't quite what I was trying to do. There we go. Log in. Under My Courses. Okay, Chapter 7. Let's see if I have the applet listed. Yeah, simple random sample applet. And then if you click on that, what happens is on our book site, they've got these little applets. I've shown you some of these in class, but I've tried to make them put a link, and then now you got to find it. What is it called? Simple random sample applet. You got to look a little bit. There it is. Choose that. It'll take a few minutes. It'll come up, and then you can use the applet to work on it. They take sometimes they're Java, and so they take a little bit of time to come up. There it comes. Anyway, I'm not going to go through it right now. But this one happens to be kind of a fake lotto type thing. The whole idea is it's supposed to pick random. Okay, well, I think we should get going on Chapter 9. And Introduction to Probability. This really is a shift in gears in a way, because now, although it's not very complicated, we're going to be thinking a little bit more about very simple mathematics. A lot of fractions here. And while I certainly am not encouraging any of you to get into any kind of gambling, I don't think you'll ever find somebody who knows math that will be a gambler, because they realize how absolutely rotten your chances are of winning, okay? I actually prefer taking my money and pouring it down an open sewer. It's about the same thing, but sorry. There are some, for example, you're going to hear me talk about this. There are actually some lottery games where you have a better chance of being struck by lightning twice than you do have of winning, and that's what I mean by why would I possibly put money in that? But I'm not. Anyway, just personal thing. Okay, I don't like throwing money away. But chance is so heavily tied with gambling that a lot of our comparisons, our kind of our learning situations will be. And that's right off the bat with the title graphic I picked here is a pair of dice, because we're all familiar with that, and of course we use it for different kinds of games. And it's supposed to give us kind of a random output. That is, if they're not loaded. And I don't want to get into that, but you can actually put a little micro weighting in dice on certain places so that that part ends up down more often, which means the one you really want is up. And of course, that's called cheating. And it's not the idea, of course. But you're going to see me make some comparisons using dice today. So first, a couple points I want to make about chance. This is kind of odd, but it really sums it up pretty well. Chance behavior is unpredictable in the short run, but has a regular and predictable pattern in the long run. That pretty much sums it up. So in the short run, you don't know what's going to happen. But in the long run, if you really could stick it out for a long time, we can actually calculate your chances and how many out of a large group will be a certain way. So for example, it's like the coin flip that they do at the beginning of football games. I mean, a coin flip, if it's a fair one, is supposed to have a 50-50 chance of landing as a head or landing as a tail. That doesn't mean that if you keep track of how the coin flips have gone in the NFL that day, that you can actually predict how the coin's going to land in this next one. That's the short run. You just can't tell. Obviously, otherwise they couldn't use a coin flip. And so, but in the long run, we know that 50% of the time, you're going to get ahead. And so, the odd thing about probability and gambling. So, please note, probability describes only what happens in the long run. And, you know, that's too bad because everybody would love to know in the short, and we can't get that. Down at the bottom, the probability of any outcome of a random phenomenon is the proportion of times the outcome would occur in a very long series. So, all right, you got the picture. So, probability talks about in the long run. And there are some rules of probability that we have to get straight. A probability has to be somewhere between 0 and 1. A 0 probability means it cannot happen. It just can't happen. It'd be like the probability that the temperature will get up to 175 degrees Fahrenheit today in Milwaukee. I shouldn't say it's 0, but it's never been 175 degrees that we know of, and there's nothing that should cause it to happen today. And then on the other end, 1, if you just change 1 into a percent, what do you get? 100. 1, a probability of that is certain. So, you know, the probability that they're going to, that the Milwaukee residents will be charged property taxes this year is 1. It's certain, you know. So there are some things that are so certain. Of course, those are uninteresting. 0 chance and a 100% chance. Rule 3. The probability that an event does not occur is 1 minus the probability that it will occur. So if the chances of, let's say, rain today were 40%, then the chances of it not raining are 60%. It's simple. It's just 100% minus that. Or in terms of whole numbers, 1 minus that. The probability of getting ahead on a fair coin flip is 0.5. So what's the probability of getting a tail? 1 minus 0.5 or 0.5. If 2 events have no outcome, down to the last rule now. If 2 events have no outcomes in common, the probability that one or the other occurs, or, I should circle that, this is a very important part of this particular statement here. So if two events have no outcomes in common, the probability that one or the other occurs is the sum of their individual probabilities. Okay, so I guess let's take a single, imagine I have a single die, and it's fair, and I roll it. Okay, what are my chances of getting a 1? Well, there's 6 possible outcomes, right? And a 1 is one of those, so wouldn't it be 1 out of 6 or 1/6? What are my chances of getting a 3? 1/6. So what are my chances of getting a 1 or a 3? According to this, 1/6 plus 1/6, the sum. Why? Because me getting a 3 has nothing to do with me getting a 1, right? I mean, they're if I do a separate fair shake, I got 1 is not influential at all about the other. So, what's the probability of getting a 1 or a 3? It would be 1/6 plus 1/6, 2/6, or simplified 1 out of 3. Okay. So, just real quick again, the 4 rules. Probabilities have to be positive. They have to, well, or 0. They have to be between 0 and 1. They just can't be anything else. And all outcomes together have to have a probability of 1. So in other words, if I take the probability of a 1 and the probability of rolling a 2 and a 3 and a 4 and a 5 and a 6, they're all 1/6. When I add them all up, I get 6/6. You get the whole thing. So probabilities have to always add up to 1. The probability that an event does not occur is 1 minus the probability that it does. And if two things have nothing in common, the probability of one or the other occurring is the sum of their separate probabilities. Okay, let's just do some more of this dice thing. Now, instead of shaking 1, let's shake a pair. And let's talk about what's the probability of rolling a 7 or an 11. Okay, so if you were just had a pair of dice and you get one shake, what's your chances of rolling a 7 or an 11? Well, the first thing we got to do is figure out, let's just do them one at a time. What kinds of things will give me a 7? Well, I could get a 1 on 1. I'm going to just separate them with commas. My 2 dice could be 1 and 6, right? 2 and 5. 3 on the first dice, 4 on the second. I could have it reversed like this. And I think that's it, isn't it? For one pair of dice, are those the ways I can roll a 7? Can't get a 7 and a 0, right? Okay. How many are there? 6 ways to roll a 7? Okay. How many ways are there for a pair of dice to come out? Well, each dice has 6 possibilities. 6 times 6 is 30. There's actually 36 possible dice rolls. I'm not going to put them all out here, but you can. I mean, there's a lot more that we never talked about, right? Like 1 and 1, 1 and 2, 1. There's altogether there's 36. Okay, now how about an 11? How many ways are there to roll an 11? Well, we could get a 5 on the first dice and a 6 on the second. We could have that reversed. I think that's it, isn't it? Aren't those the only 2 ways? I believe so. So, altogether, how many ways can I be successful in getting a 7 or an 11? 8? And 8 out of a total, like we said before, of 36. So there's my chances for getting a 7 or an 11 on a fair shake. We could simplify that. like to get that down to a little bit lower terms. What, can we divide by 4? So 2 out of 9. Okay, and you could change that to a percent if you like percents better. Okay, so you could just divide 9 into 2. Let's see, what do we get? If we divide 9 into 2, 9 times 2 is 18, 20, and then again, 9 times 2, it looks like it's going to be what, 22.2% chance. Okay. Now, something I want to get straight, because this is very confusing. The difference between probability and odds. You hear a lot about odds. There's nothing wrong with either one of them. It's just that they don't tell the same thing. Okay, now let's just take that example I just gave you. The probability of rolling a 7 or an 11 was 8 out of 36, right? Okay, 8 out of 36 in the unsimplified form. The odds of rolling a 7 or an 11 are 8 to 28. As you can see, the numbers aren't even the same. Okay, here's what's happening. You already know what probability says. It's how many chances do I have to succeed out of how many chances altogether do I have for outcomes. Odds, on the other hand, gives us chance for success compared with chances for failure. So, for example, what are your chances of pulling an ace from a deck of cards? Well, there's 4 aces, 4 out of what, 52? Or simplified, 1 out of 13. Okay, what are the odds of pulling an ace? Well, I've got 4 chances to succeed, and I have 48 chances to not. So the odds are 4 to 48. You see the difference? So success to failure, that's what odds is. Whereas probability is success to total. So probability, success to total. Odds, success to failure. Another one, flipping a coin and getting ahead. As you know, 1/2 is the probability. The odds are 1 to 1. In other words, if I flip a coin, there's 1 chance to be right, and there's 1 chance to be wrong. 1 to 1. So, just I wanted you to be aware. I don't even know if the book goes into this, but I had a lot of people asking questions about odds, and I thought I'd better go into it. What is the chance of rolling a 3 with 1 die? 1 out of 6. What are your odds for rolling a 3 on 1 die? 1 to 5. Okay. Anyway, you get the idea here. So, this won't be in the book. I think you make sure you have a little bit of something on this. Okay. Now, using the rules of probability, which of these is a valid probability model? Okay, so look at them by columns. Well, why don't we just take column 1? What if the probability of rolling a 1 was 1 out of 7, and the probability of rolling a 2 was 1 out of 7, and so forth? Is that a valid probability model? Well, they all have an equal chance. This is good. Anybody see a rule that's violated? I'll give you a hint. It's a little bit hidden. What should happen when you add up all the probabilities? Shouldn't you always get a 1? What happens when you add these up? You get 6 7s. So it looks good, but this is no good because it's got a total 1. Okay? How about this one? These total 1? Even though this dice is obviously loaded, there's no chance of getting a 4. what do we have? 1/3 plus 1/6. That's what? 2 6, 3 6, 4 6, 5 6, 6 6. At least from totaling 1, this is legit. But it's all goofed up because I don't know why. Somebody wiped the 4 off one of the faces or what. How about this one? 1/3, which is 2 6, 3 6, 4 6, 5 6, 6 6, 7 6. This is impossible. Can't be. And this is really wacko. The total has to be 1. How do you like this? A 200% chance that you'll roll a 6? That doesn't even make sense. How do you get a 200% chance of something? Again, probabilities have to be between 0 and 1. So, and there's a 200% chance of getting a 3 too. Now that should really tell you something's wacko. They're telling you this is certain, this is certain, this is double certain, this is certain, this is certain, this is double certain. Somebody's really doing this. That sounds like I bet that column came from a used car salesman. You know, the one that says, oh yeah, this is a perfect car for you. Got great mileage, you know, all of that. Yeah, every car is perfect. Okay. So, don't forget about the ruleability. That's what this reminds me of. Okay. Now we want to talk a little bit about probability distributions. And this is what? This is a flashback. We've already talked about this before, haven't we? You know, maybe we didn't call it that, but this one, which we studied in Chapter 3 and keeps coming back and will keep coming back, the normal distribution, it is a probability distribution because the total of everything under that curve is always 100%, which is 1. And as you already learned, the total of all probabilities has to be 1, and a probability, so this qualifies. Okay, and then any other curve, I don't care if it's straight on top or whatever, as long as the total area is 1 underneath, it qualifies. So this one here does not qualify because we have a width of 0.4, we have a height of 1, 1 times 0.4 is 0.4, this is not 1. So this is not a probability distribution. Likewise over here we have a width, an area of 0.5, and here we have an area of 0.2. The total area is 0.7. No go. Let me scroll here so we can see this a little bit better. Remember, we learned to call this a density curve. It's another name for a probability curve. And it is possible, although you don't have a legal one here, can a probability distribution just be a straight bar with a flat top on? Yeah, as long as the area underneath the curve is 1. And we have a special name for that. I think this was even on test 1. So it's revisited. It's often called a uniform distribution or a uniform density curve. I would also accept the term a constant distribution. And again, if the area is 1, then it's a probability distribution. Okay, just kind of a little side. I don't know if you notice these things in the book, but they have these little things in the margin. And every once in a while, I will highlight one of them. This one called Sunspots, Tree Rings, and Statistics. Let's just read this. Ancient Chinese astronomers recorded extreme sunspot activity with a peak around 1200 years after Christ. Mesa Verde tree rings in the period between 1276 and 1299 were unusually narrow, indicating most likely a drought or severe cold spell in the region at that time. A cooling trend could have narrowed the window of frost-free days below the approximately 80 days needed for cultivation of aboriginal corn and beans. Is this the reason the ancient Anasazi dwellings in Mesa Verde maybe were abandoned? Is there a connection with the extreme sunspot activity? Actually, just this interesting point that statistics actually, in this case, help us find out the answers to some historical questions. Um, it could be that there was a big global freezing going on at that time. And by the way, it's kind of interesting, Mr. Gore, who actually, I can't believe this, won a Nobel Prize for what he did. I think he did some good things, but he sure doesn't know much about statistics. He did some out-and-out false things in his famous award-winning video, which I'll show you later on. He doesn't, I hate to say it, but he doesn't understand how to read graphs. But anyway, he completely ignored the tree ring record. And the tree ring record is known to be quite accurate. I mean, when the tree rings are bad, that tells you something really extreme happened to the environment. Like they said in this, we don't know if it was really cold or there was no, there was no rain or what, but there was a lot of that was ignored. Okay, now I have a really weird assignment for you for next time. Okay? And so I want to make sure you understand this. Here's your assignment. You have two alternatives. You do not have to do both. You are to either, one, flip a coin 200 times and record the results. And what I'd like you to do is write H for heads, T for tails. Okay? In order. Now, I just want to count. So, in other words, head, H, tail, T. Okay? Or you can work with a partner and have them flip and you write. Okay, that's one way to do it. 200 times, so you got 200 H's or T's. Okay, and I want you to put them in order so I know what sequence they have in. Or you may do number two. You can pretend to flip a coin 200 times and simply write the letters down. You don't usually get an assignment like this, do you? Okay, now, the thing is, I don't want you to tell me, when you come to class, I don't want you to tell me, until later, I don't want you to tell me if you faked it or you did the real thing. Okay? Got it? So, you should come to class with a piece of paper with 200 H's or T's on it, in order. And I don't care if you get them the real way or the fake way. But I would really love to have some of you do it. I'd like to have some of both. Okay? So I'm not encouraging all of you to just fake it. I'd like some of you to do the real thing, but I'm not going to assign anything. Okay? Now I know that's putting a lot of pressure on college students because in order to do this, you actually have to have a point. So I realize this could cause a problem, but if you need a little help with that, I have a few in my office. I'll lend them out. Okay, we're done a little early today. Thank you.